compass's magnetic needle determines direction by aligning itself with the Earth's magnetic north and south poles.
If I place this in a little cup and allow it to float on some water so it's free to rotate, the compass will turn around and align itself pointing at the South Pole. If I reverse the magnet, the compass senses that the pole has changed and points the other way. Reverse it again, it swings back around.
By the 13th century AD, the compass changed the face of sea travel, relieving sailors from plotting their courses solely by the sun and stars. When storms obscured the skies, they could still ably navigate. In the centuries to come, the curious began to slowly unravel magnetism's mysteries. William Gilbert, physician to England's Queen Elizabeth I, led the way in 1600 with his landmark treatise, De Magnete. It was Gilbert who first concluded that the Earth was indeed a giant magnet. More than 2 centuries passed before an accidental discovery produced the next crucial breakthrough. In 1820, Danish physicist Hans Christian Ørsted stumbled upon magnetism's inextricable relationship to electricity.
Hans Christian Ørsted was the first to demonstrate that electric current down a wire would produce a magnetic field. He just had a compass needle near a wire. When the current went on, the compass needle turned. When the current went off, the compass needle turned back.
And he thought this was very curious. This discovery tied together 2 separate disciplines, electricity and magnetism. Ørsted discovered that they're really one and the same thing.
A decade after Ørsted discovered that electricity creates magnetism, English scientist Michael Faraday demonstrated the reverse, that magnetism can produce electricity. He found that moving a magnet near a stationary coil of wire or moving a coil of wire within a magnetic field induced electric current.
The oscilloscope is connected to the coil, and it reads the voltage that is induced in the coil. So you can see as I move the coil through the magnet, the spot moves up and down in response. The faster you go, the greater the voltage. So if you need more electricity, you have to move it faster.
Faraday's discovery was monumental. It paved the way for the invention of the electric generator, which enabled man to create electricity on a scale never before imaginable. The key to generating the power was to harness some form of mechanical energy in order to put the magnets or electric coils into motion.
In a hydroelectric plant, it's water falling over the dam through the sluiceway and turning the water wheel. In a coal-burning power plant, the coal makes steam and the steam turbine turns the generator. A wind power generator, the wind turns the blades of the generator. So the process is the same, mechanical energy converted to electricity.
In the early 20th century, magnets were also empowering the reverse of this process, driving electrical motors that converted electricity to mechanical energy. The motors had eclipsed steam engines as the era's prime movers, propelling everything from trolleys to cranes to elevators. In a common electric motor, an electromagnet called the armature revolves between the north and south poles of a stationary magnet called the stator. The armature rotates until its north pole is opposite the south pole of the stator. The direction of the armature's current is then reversed by a device called a commutator, changing its north pole to a south pole. The 2 south poles repel each other, pushing the armature forward. The current reverses every half turn, keeping the armature in motion by frustrating its effort to bring north poles near south poles. Magnet-driven motors and generators accelerated the 20th century's modernization through electricity. 2 inextricably linked industries powered one another's advancement.